When an object's on an inclined plane, we're going to need to resolve the force of gravity into both parallel and perpendicular directions, which means we're also going to need to sum the forces in both the parallel and perpendicular direction. Now I want to take a closer look here at these forces. So we have the downward force of the Earth on the object. Now, regardless of whether it's on an incline or not, that force is straight down toward planet Earth. However, since this object is on an incline, we need to resolve the force of gravity into perpendicular and parallel components. Now, if I translocate this parallel vector, we can see that this is the force of gravity that is down and parallel to the inclined plane. Now let's take a little more look at our angles here. We're at a 30 degree above the horizontal. I have a smaller right angled triangle within a larger. That makes this angle 60 degrees, and our other side of mass gravity perpendicular is a 90 degree to the incline, and because these must add to 180 degrees, we can see that our angle theta is inside the right angled triangle, and of course our remaining 60 and 90 degrees. So we are going to use trigonometry to resolve the force of gravity, i.e. the resultant vector, into parallel and perpendicular components. So now that I've gone over this angle theta and the geometry, let's use a sine function to relate the opposite side to the hypotenuse, which means we can rearrange this to solve for the parallel component of the force of gravity, which is equal to mg sine theta. And likewise, if we want to use trigonometry to relate the adjacent side to the hypotenuse, we can find the force of gravity perpendicular, which is pretty cool because now we can sum the forces for an object, noting that the force of gravity perpendicular is actually equal in magnitude but opposite in direction to the force normal. So force normal does not equal mass times the acceleration due to gravity, as it would for an object that is horizontal. It now is a component of the force of gravity, moreover, mg cosine theta, which means force normal is always going to be less than mass times the acceleration due to gravity for an object at rest, no other forces acting upon it. Okay, so let's go ahead and draw and label forces acting on this object, and let's also sum the forces in the parallel perpendicular direction. I hope you are underlining the word rest. If it is at rest, it is stationary, and that has a lot of implications as well. All right, so first I'm going to resolve the force of gravity. We have force of gravity perpendicular, or mg cosine theta. We have the force of gravity parallel, or mg sine theta. We have force normal, which is at a 90 degree angle relative to the inclined plane. And because this object's not moving, there must be some force that is equal in magnitude, opposite in direction to the force of gravity parallel. And there is. It's the force of static friction, because this object is stationary on the inclined plane. If it was frictionless under these conditions and we removed force of friction, again, it would be accelerating down the inclined plane. But in this instance here, the force of static friction is matching the downward parallel force of gravity, which means we haven't quite reached that force of static friction threshold that we talked about in previous videos. Summing the forces parallel and calling down and parallel positive. Remember, you define your coordinate system. I am calling down and parallel positive direction, which means I will subtract the force of static friction in my summation. Now, is the object accelerating in the parallel direction? Of course not. Which means the right side of this equation becomes 0, which means we can say force normal is equal in magnitude but opposite in direction to the perpendicular force of gravity. Okay? And that's pretty cool stuff to look at as well in both perpendicular and parallel. Likewise, force of gravity parallel is equal in magnitude opposite in direction to the force of static friction, because this object simply is not accelerating in either the parallel or perpendicular direction. So in this video, I've gone into another situation where we have an object on an incline, so you're learning to analyze these different scenarios and sum the forces and draw free body diagrams in these various scenarios. And I'll see you guys in class.